So for this last video, I want to talk a little bit about the Navier-Stokes equation. It's considered one of the million-dollar equations. It's, I think, an important lesson for us scientists, or just in general learners, to kind of understand. So what the Navier-Stokes equation is, or when it first came about. So where the terms come from, Navier-Stokes, are Claude Louis Navier, who first introduced this term called viscosity into how fluids momentum is affected. Viscosity is a fancy term for friction or fluid friction. You can think of water is viscous in the sense of, you've ever seen the dome that water can have at the top of like a glass. People can kind of create that dome. Water's polar. It has attraction forces within the molecules of the liquid. So there's a certain viscosity to it, or frictionish, that kind of keeps things together. And then Sir George Gabriel Stokes expanded on Navier's ideas and kind of refined the equation. And then we got the full form of the Navier-Stokes equation. So you will notice there are a lot of symbols and terms here. I am not going to make you guys use this equation. I'm not going to test you on the equation. It'll never come up in a homework problem, but I think it's extremely important for us to learn from. I am going to try to briefly break down its component parts so you understand just in general a little bit more about what this equation is. So as previously before stated, this is the momentum equation of fluids. It explains how the ocean moves and interacts. It explains how the atmosphere moves and interacts. So you can imagine this equation is extremely important in understanding oceanography or climate. Meteorologists who study climate patterns, atmospheric pressure, predicting weather patterns know this equation like the back of their hand. They have it memorized. I use this equation in most of my El Nino research. It's a very important and pivotal equation. The first term, the term in red, so again, we're not going into detail. And this is actually only one of the technically three equations. There are three, one for each dimension, because it's three-dimensional. This is the x-directed momentum equation. Anyway, the equation in red is the local acceleration. This has to do with just the general force of how fast the water is speeding up or moving. The blue is convective acceleration. What this means is, even though you could have a constant steady flow rate of a body of water, certain particles within that body could be moving at different speeds. This is how you get whirlpools or water moving in different directions. It's not always a straight pattern. Green is the Coriolis force, or Coriolis term. This is from the fact that Earth isn't stationary. Earth is moving, and that moving affects the way water moves. Now, if you're thinking the Coriolis effect between how a toilet swishes water, that's a myth. But there is actual scientific evidence behind the Coriolis effect on like big oceanic bodies of water. This is actually how we get Rossby waves. Not that you need to know what that is, but they're really cool. You should look them up. The purple is the pressure gradient. Pressure at the bottom of the ocean is a lot more intense than pressure at the top, right? Which is why we can't swim at the bottom of the ocean. We would crumple. Like, the pressure's too great. And then the last term in yellow is the viscosity term, or the frictional term, because not just water. I know I'm saying water a lot here. It's probably the one I'm most used to with salt water particularly, but there's a viscosity term between the particles wanting to stick together, or as they move across each other, creating friction. So it's kind of you can think of fluid friction is a good way to think about that. But that's kind of the general bits for understanding this part of the equation. Now, did you need to know all that? No. Why I'm pointing this out to you is, you'll notice there's so many things involved in just how water moves, or a fluid moves, more things than you didn't even think to account for. So many, in fact, this is not solvable. This is why this is called a million-dollar equation, is there's no known exact solution to this. So now you might be asking me, well, what good is an equation if it's not solvable? If there's no actual known or exact solution to this, how is this helpful at all to us? There are actually very few problems in physics that are actually fully solvable. Some of them are So these are some of the fully solvable problems. So like uniform motion that we've looked at, constant forces, the inverse square law. This is from gravity and electrostatic force. We haven't talked about electrostatic force yet, but we will. Both of them, though, are so two of them are two of the four fundamental forces of the universe, which explains literally half the forces that make up the universe. Those are solvable. And then harmonic oscillation, and then also rigid rotation. We won't get to rotating motion in this course. We will look at harmonic oscillation when we look at waves. But these are just a few of the things that we can completely solve. So you'd be actually surprised as physicists, engineers, things like that, how many things take approximations, not guesswork, approximations. So going back to the Navier-Stokes equation, it's not completely solvable, but we can put boundary conditions on certain parts of the equation then to make it solvable. So this is a topic that I'm fairly passionate about. I've done extensive research and study into what's called ENSO, which is the El Nino Southern Oscillation. It's a climate oscillation over the Pacific Ocean, and it affects the climate and weather across the globe. It can create monsoons and droughts. You'll remember back in 2016, either you may or may not remember it, we had the largest ever recorded El Nino year on record. What it is it's kind of like an offset of this oscillatory cycle. It has a lot of chain reaction effects, but the system is what we would categorize as chaotic. It's not linear. In mathematical terms, linear just means we can't really model it or predict it. In fact, there's actually no predictable model out there that will with 100% accuracy predict when El Nino is going to occur. This oscillatory cycle, NASA's got one that's about 20 to 50% accurate. Part of my work and research was creating a model using a set of equations to try to create a predictive model. It's not been tested or theorized yet. We're still working on trying to get it published. So we'll see how predictive it is in terms of percentages for that. But by studying these equations and delving more into them, we can learn more things than we ever knew before. And eventually, hopefully, one day someone solves this, which is why the Clay Mathematical Institute has listed this as a $1 million equation. It's one of 6 $1 million equations, meaning the person who actually solves this equation gets $1 million. It's kind of their incentive to try to figure out things we don't know. Currently on the list, there's actually only one. It used to be 7. One of them was solved. I can't remember the exact year when it happened. You're welcome to go to their website and take a look at it. It's very fascinating. But this is so important, and part of the reason I love being a scientist and I love studying physics is there's so much we still don't know. There's so much we can learn from equations, even if we can't fully solve them. And it takes brilliant minds or people who are passionate about it, like you or me, to just try to figure out what it could be or where we could go from it. So I hope maybe, if anything, this inspires you to get somewhat creative into where science can go and how we can make it better, how we can make our predictions better, how we can make our equations better, how we can help the climate across the globe, how we can, essentially fix certain systems or be able to understand them better.